Good afternoon. Welcome to my 7th lecture in quantitative finance. First of all, I would like to know if there are any questions concerning the RFM exam, about the results, any surprises or any comments. I mean, for my part, it was actually quite alright. I mean, there were quite some people who got full points for my part, and unsurprisingly, those got also a lot of points from my colleagues' part, so there's obviously a correlation going on. So people who perform good in my part, they tend to perform as well good in other parts. Yes?
Sorry, which exam?
The RFM exam.
Okay.
Yeah. So of course I got some emails then in the wake of the exams, but unsurprisingly that those people are obviously those who were in Helsinki and then try to write the exam, and yeah, I mean, what can I do? I mean, you choose, I mean, they choose what to do, you know, if they choose to work instead of going to lectures, then it's of course their choice. But it's of course not a surprise, you know, if you don't go to lectures and you don't, you know, you just read the papers that you actually don't know so much about the what's going on actually. So, but yeah, it's a choice what you make. Last time we were talking about some trading strategies based upon the CAP-M. We were sorting stocks, portfolios depending on their alpha and depending on the abnormal return. Yeah. Again, we were assuming that the CAP-M holds. You know, then we were regressing each stock. We used an in-sample time window as a sort of learning period. And we were determining the abnormal return, the alpha that each of all stocks generated. Then we were sorting those stocks into portfolios. We went long on a portfolio of stocks that had the highest alpha in our portfolio, and we went short on those stocks that had the lowest alpha in our in-sample period. Assuming that this model is true and that it holds also in the out-of-sample period, we would expect that the portfolio of stocks that generate abnormal returns in the in-sample period would also generate abnormal returns in the out-of-sample period. Yeah. So, and of course we know already there are many issues with this trading strategy, and it's just for illustrative purpose that I go through it here in this course. And of course in real life you use much more sophisticated trading strategies. Yeah, it's just that you get an idea about how you would set up this in general. Yeah. And of course, we know already from the beginning of this course that the alphas, that the parameters are not like stable. You know, that there is obviously a time variation going on. So the market sensitivity is not always the same, and obviously the alpha is not always the same either. So depending on the sample period. Yeah. So, and what we want to go through today, or our topic of today's lecture, is volatility clustering. Yeah. So you know from econometrics classes, you know, we know from our basic assumptions, we have been assuming, if we again use our regression model, yeah, where y, t denotes the success returns, let's say stock I at time t, and with the corresponding alpha here, beta, and here we have the market factor, and at this point we have t, and we have the certain specific component of the error as well. And we're assuming, in the beginning of the course at least, that the error term of all stocks, sorry. Yeah. So that the errors here are across time, they have the same distribution. So if t is 1 or t is 2, they have the same distribution. So they are normally distributed. With a certain expectation, and this is 0 in our case. and the standard deviation of sigma squared. And we can also here include actually index I, because this is of course individual for, it depends on the stock. Yeah. This is the error for the firm specific part, and this is the variance of the firm specific error here. Yeah. And we assume, as we see here, there's no time index. So it's across time the same. If you would write a timeline here, and because the answer is 0, it would look something like this. Yeah? It's an unsystematic error which goes around, circulates around 0. And each distribution here, you can write a probability distribution would look exactly the same. It would have the same shape, like you said, this normal distribution here. Yeah. So, but that's obviously not reality. If we look finite time series, they look pretty much different. Yeah. So we have periods where the error is little, and then we have periods where the error is very volatile, where the variance is very high. And then again, it's very little. Then again, we have periods of high volatility. So this time periods where the volatility is high and low is alternating, it's clustering. It builds volatility clusters. And this is how real life looks like. But all of our assumptions, or our model assumptions, rest upon the assumption that the distribution is normal and that they are that they are not clustering. Yeah? And I have here as an example, I have plotted here the weekly gross returns of Nokia from January 2004 until December 2013. Yeah? And this is also what you see here in this picture here. In the beginning of the sample period, we had a time period where the volatility was very low, and then we had a period where the volatility was very high. Yeah? Here we remember this is probably the dot-com bubble crash here. Yeah. And then the volatility went low again, stock prices were rising, and then we entered the financial crisis period where the volatility again went up. We have clusters where the volatility is high and clusters where the volatility is low. Yeah, and this is not only for Nokia, this is for any stock, the same thing. Yeah, this is an empirical stylized fact. So, given this time period, so I estimated the mean of the series, of this recurrence series, was 0.62% per week, and the volatility, the weekly volatility was 8.85. So what I did then here is I used this data here, like mean 0.62 and the standard deviation of 8.85, and then you can simulate the time series in Matlab. I think you can even do it in Excel. And this is how a time series, or how the evolution of a random variable would look like over like using the same number of observations that has a mean of 0.62 and the standard deviation of 8.85. It should look like this if it's distributed as we assume it should be. Yeah? If there is no volatility clustering going on. Here we say the volatility or the random variable is homoscedastic distributed. Homoscedastic means it's the same. In this case, it's heteroskedastic distributed. It's not the same, it's clustering. And here I plot those time series together. And you can see they are somewhat overlapping, but it's not really the same pattern. So our new assumptions are now a little bit different. So we have the same approach. We assume again linearity like earlier. That's the same. our matrix notation doesn't change either. We also assume that the stock market return is strict exogenous, so that we can derive our model easily. So we also assume that our regressors are not perfectly correlated, so otherwise we have problems to invert the matrix. And now we assume, in contrast to the earlier assumption, that the variance of each error term across time has a different distribution. That's now our clustering assumption, so to speak. But at least we assume that the errors are not autocorrelated. So we say, okay, the variance may vary over time, but we do not allow for autocorrelation, which would look something like that. You might remember from econometrics, if we have autocorrelation, the errors would look like this. They move around a little bit, but in a systematic pattern. And if we would have autocorrelation, and this is maybe first order of autocorrelation, if we would observe this kind of patterns, this would mean that if there's a company that generates high excess returns or a high firm-specific part of the excess return, the stock would be likely to generate high excess returns in the next period as well, and would trade on it. So the market would be not efficient if we would have these patterns in error terms. Moreover, we would need to use that information and to incorporate it in our point estimator. So we would use a different point estimator. It's so to speak DLS estimator. The generalized D-squared estimator. So we say, okay, we do not allow for autocorrelation, but we allow for heteroskedasticity. So, and what's the impact on our point estimates if we have this time series here? If we have volatility clustering, what's the impact? Why would we bother talking about that anyways? So, and now we have to go back to the third lecture or fourth lecture, or when it was. And I told you earlier, if you work in the industry, if you work in a bank or so, you have to ensure that you report, or that what you report is robust. So, I have to get my notes here. And that's of course a classical question also for the exam, because you're the first course obviously who has an exam as well. So again, we have our standard model here in matrix notation. So we have derived now many times the point estimator. And we have to transpose our regression matrix. Times itself inverted, times the regression matrix transposed, times our excess returns. And we have to run this model k times if we use k different stocks. Then we get always a new point estimator. And if we have the cap n, then we remember that our X matrix looks like that. And we would include also constants. Then we would have a vector of ones in the first column of our X matrix, and the excess return of the matrix vector in the second column. So this is the excess market vector for time t is 1, time t is 2, the second element, and the last element is the excess return of the market vector at time capital T. So what we we have is the T1 matrix here in this case. We would use the Kalman Fairness 5-factor model, and then the intercept term, then we would have more column vectors here, and this would be T by 6 matrix then, yeah, of course. So what we also know from our model is we can easily get the estimated residual vectors if we estimate our our parameter vector using just the input data. Then we can put it in here, bring this guy here on the other side, and we would get the estimated residuals here, very easy. Using our estimated parameter vector here. Then what we are also talking about is if we take the expectation of, want to know how good is our point estimator. So we take the expectation of this guy here. So, and of course what we can do is then we can plug in this formula here. And we have seen, or we have seen that what we get is the expectation of the real beta plus. Let me just take a look at this here. Plus this term here, x transpose x inverted times x transpose u. So now we can bring across this guy here on the other side. So what we get then, and we can also put it into the expectation operator because it's just a number. With the expectation of our point estimator minus the real estimator, which is beta, is then equal to x transposed x inverted x transposed u. So this is what we have already been talking about last time, or two lectures ago. This is actually what we get just by our OLS, or what we can derive by our OLS, simple OLS framework, our OLS point estimator. Yeah. So we were also talking about the covariance, or point estimator. What's that guy? And we know already that what we have to do is we have to take the expectation of this guy here. Times itself transposed. That's the general formula of the covariance. And what we then have to do is, knowing this one, this equality here, that this equation holds, we can just plug in this guy here. What we get then is the expectation x transposed u transposed x. So this is what we have derived already a couple of times in this course. So, and what we knew with our assumptions hold, that's the random part here in our equation. And before, we know what that guy here is. It's a matrix, it's a T by T matrix, because this is a T by 1 vector times itself transposed. So what we have here is a T by T matrix. And we know that according to our assumptions, we have the sigma squared on the main diagonal, right? And everywhere else has zeros. our assumption was that sigma 1 square is equal to sigma 2 square, which denotes the time index. The sigma 2 is equal to sigma square at time t. And that was our assumption. Assumption. This is what we had assumed earlier. So if we have that, if this would be true, if we would have homoskedasticity going on, what we can then do is we can move the sigma square out of the matrix, because it's anyway the same, and it's in just a number. Here. We can move it out of the matrix, sigma square. What we have left is a matrix that has only once on the main diagonal. And I again apologize for my handwriting style here, but I'm left-handed, so easy. So what we get is the identity matrix here. Yeah? So we move sigma square out. What is left is a matrix that has only ones on the main diagonal and zeros anywhere else. So it's the identity matrix of dimension t by t, of course. And we know already, if this is the identity matrix here, this guy here disappears. Yeah. And what is left basically, if we will solve the equation, what is left then is sigma square times x transpose x inverted. Yeah, and that's that's the covariance. Of our beta hat. Yeah. You remember that, right? That's what we have already derived a couple of times, a couple of lectures ago. So, and we know also this guy here, how we can get it off the data. This is just the residual vector. This is the scalar product of the residual vector divided by t minus the number of regressors. So that's also given by the data. And this is also given by the data. So if we use the CAT-M framework, then we know that our X is a t by 2 matrix. So what we have here is a 2 by 2 matrix. It's t by 2 transposes 2 by t times t by 2 is 2 by 2. If we invert 2 by 2 matrix, it of course remains a 2 by 2 matrix. That's the number, that's 2 by 2 matrix. And what we get is, we have a 2 by 2 matrix. We remember that with 4 elements here. And we remember, if we take that on the main diagonal of that matrix here, that we get that the first element is the variance of the alpha of the upboundary term, and the second element on the main diagonal, using the CAT-M, is the variance of the point estimator for the market sensitivity. And above and below the main diagonal, it's the same element, because the covariance matrix is symmetric, which is a typical characteristic of it. And we know that this is the covariance between the alpha and the beta. So if we want to get the t-statistic, we would, for the alpha for instance, we would take the first element of our parameter vector and divide it by the square root of the first element of the main diagonal of our covariance matrix of the beta. If we want to get the t-statistic for the second guy, we take the second element of our estimated parameter vector and divide it by the square root of the second element on the main diagonal. That's how we get the corresponding t-statistic. And then we can make a statistical inference about the methods, about our point estimates. So that was easy, right? So what happens now? Our new assumption. The assumption is that sigma square times t1 is is not equal to sigma squared at time t2, and it's not equal to sigma squared time capital T. So what does that mean? What does that mean? So it means that we cannot do this operation here, because on the main diagonal the elements are not the same. Let me get the green one here. This is maybe clear what's going on here. So this matrix here looks now like this. It is sigma squared from the first observation, from time t is 1. Then we have sigma squared time t is 2, and so on. And the last element of the main diagonal is sigma squared of time capital T. And of course, because we said already, okay, we assume that the errors are not autocorrelated. So we have above and below the main diagonal again zeros. So that's not the problem, obviously. But the problem is that we have to take now, we don't know what is the expectation of this guy here. We cannot simplify this equation anymore like we did here. That's now not possible anymore. So we have to take the expectation of what is here on the main diagonal. These are different elements for each point in time. We have a different variance here of our errors. So but what can we do? So in there's a paper, a 1980 paper of White, who suggests that we can proxy this matrix here. Let's call this matrix here omega. And we can estimate it from our data. Or we can use, for instance, this first guy here is simply we take the error from time t is 1, the estimated error, and multiply it with itself. And the same we do for the second element of the main diagonal. We take the error, the estimated error, and we get the estimated error from this equation here. Given the data, we run the OLS estimator, we get the error, we get the vector of error terms, and then we take element by element. First we square the first one, then we square the second one, and the last element is just the last error term squared. For the last estimated error terms squared. So on elsewhere we have zeros. So that's of course the same as if you would just square it. Step here that we easily can retrieve. Take the first element, square it, second element, square it, and so on and so forth. So what we get here, this guy here, is a T by 2 matrix transpose, it's 2 by T. What we have here is a 2 by 2 matrix, right? Times 2 by T, because we multiply this expression here with the regression matrix transposed with 2 by T. This guy here, we know already is T by T. This guy is T by 2. This guy here is 2 by 2, like, because it's the same matrix product that we have here. So the whole expression here is also, it's a 2 by 2 matrix. And it must be like that. If we multiply everything out here, what we get is a 2 by 2 matrix. And it must be like that because it will be, it must be the same, it must have the same dimension as this guy here. It just looks a little bit more complicated because we cannot anymore simplify it like we did here in this step. But we have now to take the whole expression here. But luckily we don't have to do it by hands. We can just plug it into Matlab. The X matrix is our data matrix, that's what we have given, everything is given. And this guy here, we just estimate after we have run our point estimator, after we've estimated our point estimator. We can easily also estimate this omega here. After we know what are the estimated residuals here, we just grab every element here and square it and put it here on the main diagonal. Then we plug this guy here into this formula here, run the formula, and what we get is the covariance matrix, like here. And then again, we focus on the element on the main diagonal in order to get our t-statistic. So here to everybody. Did you do this also in econometrics 1? You know that? Yeah, okay, that's a shame. No, but of course that's important, yeah, because this has obviously a huge impact, or it can have a huge impact depending on the data set that we have. But this can have a big impact on the t-statistics. So if you run it, or if you estimate, or you come up with a new training strategy and you run it out of sample and so on and so forth, and you want to report to your boss the profitability of your training strategy, and then you use the raw t-statistics and you find, yeah, well, I have an investment strategy that gives us, I don't know, 2% returns per month. Yeah. But if you would use the real or the correct t-statistic, it could be that the t-statistic actually indicates that this is just the white noise. There's no profitability. So, and this can be sometimes also costly if you invest wrongly. Yeah. So therefore, you have to always know what to do, and that's why we go through it here. If you just use e-views, there's also this button where you can push white correction or something, and then it gives you actually this covariance matrix using this omega here. But you actually don't know. I mean, now you know, but if you would have not gone through this here, you wouldn't know what you actually do, right? But now you know what white correction means, actually. So it means that we estimate this omega here. That we account for this volatility clustering that we see. Each residual here has different variance. Yeah. So, and now we want to know how do we do it in Matlab. Here's actually everything I gave you here. Also a brief summary of that here on the slides, but of course not so much detail. So the exercise. consider the following linear model for pricing uric acid. So it's again the CAT-M model here. We know that already. It's the same exercise actually that we have been already doing. But now we account for this volatility clustering. So implements, let me see. So does the CAT-M hold? That's the question that we're interested in. Given our data, given our stocks. And also what we also want to know is how good is the CAT-M actually in explaining our returns. So the second question aims at the R square. Last time we went already through the formula, right? And now we implement it here in Matlab. So again, we want to know how good is the CAT-M in explaining and in pricing the cross-section of our stock returns here. So we do basically the same thing that we have already done, but now we use not the old formula that we have been using like 2 lectures ago or so, but now we use this formula here. So we start everything again with X's data. You will remember our data matrix. We use always the same data matrix here in this course, so that's nothing new. Obviously, on the first column we have the gross returns of the OMX30. So we define X as the gross returns of the stock index. So we retrieve the first column vector of our data matrix. Then we want to define our gross returns from our stocks in a Y matrix. And this is also what we do. What's the second step here? This is nothing new, we have already done that. Then the risk-free rate is the 16th column in our data matrix. So we find RF as the risk-free rate as the 16th column of our data matrix. So how many observations we have, capital T, should be the length of Y, and we know already we can also write the length of RF or the length of X, because all the vectors or matrices have the same length, of course they have. Or you can, as an alternative, just write T is equal to 250, if you want. So K is 14, because we have 14 stocks in our sample. Y1, now we construct again the excess returns, because our CAT-M is defined in terms of excess returns, so we need to get the excess returns for our stock universe here. And we have already done that many times here. That's the same thing that we have already done. We create the excess return matrix by subtracting the time congruent risk-free rate of each stock. And we know already we can make it much easier here. There's just one way to do it, but what we can also do is we can just subtract the risk-free rate from each column. So we can write as an alternative for J is 1 to K, Y1 double point J is equal to Y double point J minus RF. Then we end the model as an alternative. So what we do is we go through each column vector of our Y matrix. This is what it means that J is 1. It gives you from the first column here, we know this is the column here, column index, and this is the row index here. It gives you all rows of the first column. So, and we know there are the gross returns of the first stock. So, and we subtract the vector of risk-free rate. So, and then we plug this into the first column of our Y1 matrix. And so we do for all of our K stocks. We just subtract this rate. We have already done that, and we can do both ways. That's of course the easier way But I gave you this code here in order to just to get so that you get used to how to use for loops here. Yeah. Same is of course for our x1. X1 are the excess returns of the stock index, because we need this as a regressor for the and because we can M is defined in excess terms, so we need also the excess returns of the market factor here. And again, it's the same thing. We don't need a for loop here. We can just subtract. We can define x1 or whatever you want. I told you can name it however you want. I call it x1 as x minus rs. That's not kind of you don't need a for loop. You can just subtract the risk-free rate vector from the gross return vector. Then we have it. So again, we want to have according to our model, look back here. We have the intercept term as well. So, and in our regressor matrix, that corresponds to a vector of ones. So we need a vector of ones, and let's go back here. I was a little too far. I wrote I define constant as ones of dimension t, 1. So we have in the first column, capital T is 415, so we have a column vector of 215 ones. So what happens then, and now we remember. I might take this away now. I think I need the space. Oh, but I can also use this one maybe. So remember now our X matrix. Our X matrix. As vector of ones, so the first column, and the second column, we have the excess returns. The market vector. The T. That's a T by 2 matrix. So, and we define it in Matlab like it is here. We know constant is a vector of ones, 215 ones in one column, and x1 are our excess returns of the omics 30. So get this guy here. Constant, then space x1. This is a matrix, and this corresponds to our regressive matrix. There are always different ways how to code that. What you can also do is you can just define the matrix, let's call it, I don't know, XX maybe. We can define XX as this guy here, put it outside the for loop here, and then instead of writing this matrix here, we can just write XX, for instance. XX transpose and then times XX instead of this expression here. But we have to define it then somehow and put it outside the for loop. But in this example here, I just wrote it or defined the matrix as it is. And then, so again, so we want to store our results, so we create again a matrix beta, zeros, 14,2. So because we have 14 stocks, so we create again a matrix, and I call it beta, where we want to store in our results. It's a 14/2 matrix. And the first element should be the abnormal return, or the beta 0 or alpha if you want, for the first stock. And the second element in the first row should be the corresponding sensitivity against market factor. Same thing that we have already done. And the last element here should be obviously then the corresponding point estimates for our 14th stock in the sample. So we have already done that. So that's something new. So how do we do it? Again, with a for loop from 1 to k is 14. So we get first these estimates here, and then these, and then if k is 14, we get the last estimates here. So we do 14 times the same thing, obviously. So beta underscore 1 is equal with, and then what we get here, what we have here, constant x1 transpose times constant x1 inverted. That's exactly our OS formula here. What we have here. It's the same thing. We have already done that a couple of times ago. It's this formula here. And we do this for all these 14 stocks. So what we get is a 2 by 1 vector for each stock. Yeah? And we know we have to transpose it. We have to make it to 1 by 2 vector, because this is obviously here the 1 by 2. This has the dimension 1 by 2, so we have to transpose our 2 by 1 vector and put it here. That's what happens there. So this is exactly the same thing that we have already done. So we end the first for loop here, and what we get then is we get the corresponding point estimates here that we then have stored in our beta matrix here. Yeah. So that's so far nothing new. So then what we also want to know is the R square. So how much of the variation of the excess returns is the cap M capable of explaining? Yeah. So the R square will probably vary across the stocks. But we want to know, okay, what's the average R square? So what we do is, okay, first we construct it again a vector of zeros, which has a dimension 14 by 1, or k, capital K by 1. Yeah. And I denoted it here in the code as R underscore squared. R underscore squared. So, and then also we want to store the t statistics of our point estimates. So we create also a zero matrix that has the same dimension as our beta matrix here for our point estimate. So it's, and in the code I denoted as t underscore statistics underscore beta is equal to 0, k by 2, 40 by 2. So again we get a matrix that has 14 rows and 2 columns of zeros where we store corresponding t statistics for all point estimates. So what happens then? So for j is 1 to 2. So again, we go first. First we estimate the t statistics for the upper return for the alpha or beta 0, which is what you find in the first column. And after this is completed, we estimate the corresponding t statistics of the market sensitivities, which are the second column here. So then, so we start with j is 1, and then we have the second for loop, because we go through each stock itself. So I is running from 1 to 14, or we can also write actually in the code I from I equal to 1 double point capital K, because we have defined it earlier already. So then what we see here is beta underscore 1. It is the same formula that we used to estimate our point estimates here in the earlier loop, yeah? Yeah. It's the same formula. This is clear, everybody. So this is exactly what we have here in our theoretical OS framework here. That's this guy here. So we get the point estimate for the first stop, beta underscore 1, or 7, 8, 10. We estimate the OLS residuals for each stop. So U is equal with Y1, well, so the first column of the Y1 matrix, where we have the exact returns of the first stock minus our X matrix here. Now, that's our X matrix times beta underscore 1. So we get the exact returns from the first stock and subtract the estimated exact returns. Yeah? This is here X, or our regressor matrix, times the point estimates times our beta hat is the U hat. Yeah? Or Y hat, sorry. Y minus Y hat is U hat. So this is this step. This is the second step of our OLS framework here. Is this clear to everybody? This is exactly this what happens here in the code. So then we estimate the omega matrix. This is our sandwich there. So omega is equal to 0 T by T. So the first step here is we have to create a matrix of zeros. That has the dimension T by T, yeah? Because our omega has obviously the dimension T by T. There's a T by T matrix here. As we have also noted. So first we have to estimate, we construct a matrix of zeros, and then we want to put in something here. And what do we put in here? I told you already. We take the estimated elements of our residual vector square, each element itself, and put it on the main diagonal. So this is what you see here in the code actually. Well, this is what happens here next. So first, we created omega zeros T by T. Then we define, we define omega 1, and again, you can give it any name if you write your own code. It's equal with IT. The command IT gives you an identity matrix. I means identity matrix. So I, T. If T is 250, like in our example, it gives you an identity matrix where you have 215 elements of ones on the main diagonal and zeros elsewhere. So the dimension is 215 by 215. Yeah? So the identity matrix is always symmetric. Yeah? So I transpose is equal with I. And then we have here two for loops. Yeah? We have the first for loop from small t1 equal with from 1 to capital T, and the second is I define it as small t2 is equal with 1 to capital T. What does that mean? So both for loops go obviously from 1 to 250, because our omega has 250 elements in rows as well as in columns. So, and as you see here, omega small t2 comma t1 is equal with omega 1, and we have the same index here. So it takes the same element of our omega 1 matrix. And omega 1 matrix, we have the identity matrix. So, and what we know is if t2 is 1, So omega 1 is a matrix that has, it looks like that, okay? So if T2 is 1 and T1 is 1, then we are obviously here. We want to put in something here. And what we want to end up with is this guy here. So what do we do? So we get the corresponding element of omega 1 matrix, which is this guy here. This is omega 1. It's identity matrix, which has the same dimension as the matrix that we code as zeros, where we want to store our results in. So we take the corresponding element, the first one here. T2 is 1 and T1 is 1, and we multiply it with ut squared. So ut squared is this guy here. It's ut1, right? Yeah. And this means that we square it. Yeah. So we take this guy here from our residual vector, square it, and multiply it with the first element from our omega 1 matrix, which is 1. And we put it here. And that's exactly what we want to have. Yeah. Because that's how we have defined our estimate omega. What happens then next is T2 is still 1, because I told you already that first we complete the inner loop before we go back to the outer loop. So the next step is then that T2 is 1 and T1 is 2. T1 is 1. And T2 is 2, so we are here. Right? So what's happening then? So we take this guy here, the corresponding element here, now in our omega 1 matrix, and multiply it with something here again, but it doesn't matter, because whatever you multiply with 0 is 0. And this is exactly what we have here, 0. Yeah, so it completes, so it multiplies everything with zeros here, because we have on the identity matrix zeros below the first element. And this is exactly what we want to have. And it becomes interesting then again, if T1 is 2, then we are here, then we are on the second column, and T2 is 1. Here is still zeros, obviously. Here are still zeros, because this corresponding element here is also 0. But then, if T1 is 2 and T2 is 2, we are here. And here it becomes interesting again, because what happens here is then, okay, the corresponding element here in our omega 1 matrix is a 1. Now, omega 2, 1 is 1 times ut1 squared. So, and ut1 is 2 in this case. And this is the second element of our zero vector, squared. Times this 1 here is exactly what we want to have. Yeah? Is this clear? What's going on here? There are certainly also other ways to do it. Who knows? So you can't just try. But this is at least one way how we can code this omega here. Yeah. So once we have completed, so Matlab goes through, the code goes through every element here, and what you get is then this omega matrix here, yeah, this T by T matrix. So if both for loops are completed, yeah, the last element is this guy here, of course. Yeah. It's when T2 is capital T, which is 215, and T1 is also capital T, which is 250. Yeah, then we are here. And what we plug in is, okay, we get this element here, the corresponding element of our 1 matrix. This is 1. Okay. We multiply it with the last guy, capital T squared. So put it here. And that's exactly what we want to have. So once we have estimated this guy here, now what we have to do is we plug it into here. That's our omega then. And it's an estimated omega, so we have to write it like this. So this is what happens here. Beta underscore variance is equal with, so what's this guy here? That's our x here. We know it here. Transpose times itself inverted. So this is exactly what we see here. That's the first term. X transposed x inverted times x transposed. So times, when we see these 3 small dots here, it means, okay, we continue the command in the next row. So times itself transposed times omega. And we have already estimated it earlier here in these 2 for loops here. So we get the omega that is stored still in the workspace, yeah, and put it in here. So that's exactly what we want to have here. That's exactly this sandwich here. And we put it there, we multiply it with the regression matrix again, yeah, times this guy here that we have already done here in the beginning of the equation there. Yeah. So we have to multiply it again with this guy here that we have already here in the beginning of the equation. Yeah. The regression matrix on both times itself inverted. So what we have here is, of course, it's a 2 by 2 matrix. Yeah. So what we want to have then is, okay, we want to grab the first element. Yeah, we know what comes out of this matrix here. I told you it's the same like before. It's a 2 by 2 matrix. Yeah. So what we want to have is now we want to grab. J is still 1. Yeah. So we are in the first column here, where we have the T statistics of the unknown returns. Yeah. So J is still 1. So we want to grab the first element of this covariance matrix. We have to take the square root and divide it by the corresponding, or we have to divide the point estimate by the square root of the corresponding element of the main diagonal of this covariance matrix. So this is exactly what happens here. You have seen the formula earlier here in our couple of lectures ago, but this beta underscore variance, which is our covariance matrix of our point estimates, this was different. This is now this huge term there, what we have derived. So we take the square root of this corresponding element here, and it's in the denominator here. Yeah? So this is actually nothing new. The only thing that is new is that this covariance matrix here is now estimated differently using this omega matrix. So after we end both loops, we get the corresponding estimates. So that's basically nothing new. So then we can have a brief view here on the point estimates So using the white correction, we get, or this sandwich covariance matrix that we have now used, we get this corresponding point estimates. So the 2.91 is the corresponding t-statistic of the alpha for the first stock, the abnormal return, and the corresponding t-statistic for the theta for market sensitivity is 10.11. And you can compare it with the t-statistics that we had estimated last time or 2 lectures ago. It is slightly lower. So, and you can also compare, of course, the other figures here. What you see is they are only slightly different. Yeah. So, again, we have 2 out of 14 generate obviously abnormal returns. Yeah. So, still, we would draw, in this case, we would draw the same conclusions that we have drawn last time as well. Yeah. So, the pricing model is not capable of pricing our 14 stocks. So the conclusions are the same, and in this example here, obviously, the impact of heteroskedasticity is not that huge. It actually, the impact is bigger if you compare the market sensitivities here, if you look carefully. But that's just, it could be much more severe. So the sample period was very short that I used. So if you use a longer sample period, the impact might be much more severe. So the R square, these are the corresponding estimates, so it varies between 0.11 here for the 4th stock, and we have for the 5th stock 0.62. Then we take the average here, so the average R square is 0.31. So the cap M is roughly capable of explaining 1/3 of the variation, the cross-sectional variation of our assets, of our stock returns. So, are there any questions?
Yeah, what is the null hypothesis for this? Well, we just got the 2.91, 3.8 and so on.
Once again.
Like, what's the null hypothesis? A0.
So it's the same null hypothesis that we had last time. So if the cap M is capable of pricing our test assets, our 14 stocks,
Yeah.
then the t-statistic should be below 1.96.
1.96, alright.
Yeah. So 3 out of 14 have higher t-statistics than 1.96. So, and 3 divided by 14 is something like 20%. 21%, I think. So, and if we have more than 5% of the stocks would have t-statistics that are larger than 1.96, then we would say, okay, the model is not able to explain this stock return.
Right.
So of course, in the exam, you know, when I write, okay, or when you see in the description, the assumption like here, heteroskedasticity, that the variance of each element of each residual is unequal, then of course it must, the bell must ring here that we have already to do with this guy here. That we cannot simplify it like here. So the derivation stops here. The derivation must stop here. Okay. So are there any other questions? Come on. Okay, it's late already, I know. But it's a skill to everybody. I mean, if not, you can drop by, can book an appointment, and we can derive it again if you want. That's no problem. If you want other things to derive, you can always onto my office so that I can derive to something. Just kidding. Okay, if you have no more questions, and I don't know who has put the chats here, I mean, yeah. If you have then no more questions, then you have a good evening, and then see you tomorrow.
Hyvä.